And Kapil and I are going to talk today about the real-time data ecosystem at LinkedIn. But first, we want to ask this question: what does real-time data mean? And since this is, Silicon Valley, you can actually go around and ask people what this means, and they'll actually reasonably give you good answers. So we did that, and the first person we talked to works at a streaming startup, and so obviously he said, stream processing, right? If you're not doing stream processing, then you don't have real-time data. And then we went and talked to a data integration company, and they said, real-time ingestion, that's really where it's all at. And if your ingestion systems are not able to generate and ingest data in real time, then you don't have real-time data. Then, of course, we went to an analytics vendor. They're building an analytics database that can process lots of queries super fast. And they said, real-time serving of low latency queries within milliseconds, maybe seconds. That's what you really need, otherwise you don't have a real-time data ecosystem. And then there was this one person in the corner who said, well, it all depends on the context. And he said, batch processing might work as well. I said, really? Batch processing for real-time data? And he said, well, depends on the context, right? If I'm trying to predict hiring trends for the US or for the world, real-time is being able to predict this hiring trend every day. And I don't need, 10 milliseconds latency between the time you acquire a job and when I can predict whether this particular skill is now more relevant. So I think what we're trying to convince you today is that real-time data is not just about one particular thing, but a bunch of different capabilities that kind of come together to create an ecosystem that works. And we'll try to give you a quick flavor of the different parts of our portfolio that we've kind of combined together to create a real-time data ecosystem. And some of it is open source, some of it is not, but hopefully these patterns are, they apply across different domains and industries. So the real-time data use cases at LinkedIn are very similar to real-time data use cases at a lot of internet companies. There's a bunch of in-product analytics, like if you go to your profile page and you click on who viewed my profile, you get to look at, well, who's viewed your profile. And we give you lots of analytics like, hey, are recruiters viewing you ever since you did your last blog update, or things like that. So there's a lot of slicing and dicing that you can do, look at industries, different skills, things like that. We also have advertiser insights. People can, advertisers who are advertising on LinkedIn.com get essentially real-time insights into how their ads are performing. Then there's a bunch of recommendation algorithms that are running and optimizing the site, and at that time they're using real-time features constantly. For example, the kind of creatives you're looking at, the kind of profiles you're looking at, what kind of actions you're doing on them. These are often being fed into real-time features that are used in these models to actually make decisions about what to show you next or what to suggest to you. And then there is standard monitoring and alerting applied both to operational metrics as well as business metrics. And we're constantly looking at ways to optimize the site and make it better for our members as well as for ourselves from a cost to serve perspective. So we could talk about every one of these use cases in detail, and we would probably spend the whole day here. Since we only had 30 minutes, we decided to focus on one particular use case, because at a high level, every pipeline ends up looking something like this. You have a create phase where the data actually gets generated. It's actually pretty hard to generate real-time data if you don't have a system that can give you that change stream right away. And then you ingest it into a processing system, and then you process it, and then you load it into a serving system which can actually access and the data in a way that you need it to. For example, if you're doing billions of pairwise count queries, you need a system that can handle that very fast. And in some cases, if your destination is actually super powerful and you've created the data in kind of the best way possible, you can actually skip the ingest and process phases. So in some pipelines, you can actually do away with the ingest and process and save some latency. So today we're going to focus on just the metrics computation use case, because it's actually quite fundamental to a lot of these different use cases. When I talk about feature computation, a lot of times they're actually computing metrics. When we talk about in-product analytics, there's a bunch of metrics computation there as well. So the first thing I want to quickly motivate is a platform that we've been working on at LinkedIn called the Unified Metrics Platform. And the reason we ended up going this way is, we had, and we still continue to have a ton of different metrics that show up at different places. There's the internal side where, employees or product managers, analysts, salespeople, they're looking at how the numbers are looking at right? And then the same kind of numbers are also reflected back to people, members or customers or partners who are logging into LinkedIn.com and looking at how their spend is performing or things like that. And we've had a lot of kind of fragmented data pipelines in the past across kind of this online as well as offline paradigms. And so it ended up really creating a lot of confusion because you would look at a number in one particular dashboard and you would look at kind of the same number somewhere else, and it would be somewhat different. Or you would look at a top line number that dipped by 2%, and then you would say, hey, is this really weakness in Brazil or the US or where? And when you go down into the dashboards that show details along these cuts, you see that the totals don't add up anymore to the same number. So the reason for building kind of this unified metrics platform was to converge a bunch of this metrics logic into a single place. And so the big three things we set out to achieve was, hey, we want a single source of truth for metrics. So all metrics logic must be in one place and must be verifiably deduplicatable, if that's a word. Also from an operations perspective, these different pipelines were actually causing us more hassles than helping us. Like there was a real-time pipeline, but it couldn't really do backfills very well. There's a batch pipeline, but it can't really do real-time very well, right? And then each individual pipeline ran its own queues, and so one particular pipeline might be down, but the other might be up. And so we ended up creating a centralized kind of multi-tenant pipeline abstraction, which can decide where to execute these metrics computation scripts. But fundamentally, there's a single team that's responsible for the care and feeding of this pipeline, and that's a pretty big deal. And finally, of course, we wanted to make it super easy to onboard onto this platform. So this is what the workflow looks like. It's at a high level, a metric owner decides to come up with a new metric. Maybe we are launching a new feature and we want to count exactly how many times people come to that particular page and then move on and do something that we want them to do. The metric owner would iterate on this metric, play with it in their sandbox, get comfortable with how the logic looks. They've filtered out all of the bad data. They're actually looking at exactly the right segment of the population. And at that time, they'll create this metric definition. It gets reviewed by a very lightweight governance committee, and then you check it in to a code repository. This code repository then has build scripts and other kinds of amenities so that it can deploy the metrics logic into both a core metrics job, which is computing the metric, as well as systems jobs, which are kind of ancillary to the core job. Maybe they're doing joins and a bunch of other aggregations that are necessary for serving. They're also doing things like monitoring how the job is doing and a lot of the operation stuff that I talked about. And we'll kind of talk about these in a little more detail later on. But I talked about this thing called a metric definition. So what really is a metric definition, right? So the metric definition starts with the concept of a data set. So a metric owner is really onboarding a data set, and that data set is produced by a script. So you'll typically write a script, and we support a variety of different languages. And that script declares a bunch of input data sets that it needs to process. It also declares time windows. So a bunch of this computation tends to be obviously window-based. So there's input time windows, there's output time windows, and then the data set itself is schema'd. So you can think of it as a wide table, and there's metadata that indicates on that table which columns are metrics, which columns are dimensions, which columns are entity IDs, which might need to get joined with something else later on, which of the columns is time and what unit is it in. And on the metrics, what kind of formulas do we want to apply? Do we want to aggregate them up using sum or distinct or these kind of standard aggregation formulas? And then finally, the tier in which the metric needs to run. Is the metric a tier 1 metric, which means we need super fast SLAs on it, and we want to make sure that any breakage gets alerted to the NOC right away? Or is it one of these experimental metrics which runs in kind of a daily mode, and if it breaks, you don't really page the on-call person? And the entity IDs can then point to entity dimensions that get kind of joined in automatically. So what we've tried to do really is create as much declarativeness as possible into this metric definition so that the system can optimize for where exactly to run the script and how often to run it. And then finally, there's some good documentation like metadata, the name, the description, who are the owners, because that's important, and then just free-form tags. And once you've got this metric definition, you basically onboard it onto UMP, or the Unified Metrics Pipeline. And at a high level, don't worry too much about the details. At a high level, it's basically creating a metric script, which is going to process all of your input data, create a standardized output data set, which then gets aggregated and rolled up, cubed, dimensioned, data quality rules run there. And then this data set now is available for downstream consumers to process, either in real time as it's getting generated, or as dashboards, or queryable, as a queryable serving data set. So this is kind of the end-to-end data flow. I'm going to talk about individual parts of this whole pipeline. So we'll start with, hey, where did this data all come from, right? What are the different kinds of data sets that are all feeding into UMP? So that's kind of the create phase. So the first piece of the puzzle is your databases, right? Every website needs to have one. This is where you store your accounts, your user info, user profiles. And sometimes you also store other things like what they're doing on the site. So we built a database called Espresso. It's a key document storage system, distributed. XLDB 2011 was actually the first time we talked about it publicly. It has a lot of features that you find in modern NoSQL key value / key document stores. Also supports a few extra things like secondary indexes, transactional updates to related data sets, and most importantly, a real-time change capture stream. And that is super important. It has a consistent change capture stream that's coming out of it, which allows you to subscribe to the changes that are happening to your tables and process them in real time. And Espresso at this time has pretty much taken over a large part of the LinkedIn database ecosystem. It's pretty much the default choice for anyone who's starting a new application or a page and wants to have a database sitting behind it. The second thing, of course, is besides your database data is all your log data, right? And in the old world, you would have Apache web servers and you would just mine the web logs, right? But at LinkedIn, we actually went pretty structured on this whole problem. And we said, schema first. We don't want to be parsing log files and then inferring what exactly happened. And so we created this system called Kafka, which is a high-volume pub subsystem. It has tunable guarantees around persistence. And then we essentially funnel all of the real-time activity that's happening on the site through this system. So every time you log into LinkedIn, you view a profile, even when you view a single page, there are tons of individual impression events that are firing because everything that you're seeing, we count it as something you've seen, right? And then as you're scrolling, there's other things that are coming into your view, and those impression events are also firing. So all of this stuff gets sent into what we call our tracking ecosystem. Some of it is firing from client-side devices, mobile phones, or it could be your browser, and some of it is firing server-side. For example, if we computed some recommendations to send you, well, we're going to log exactly what we decided and why. And so all of this goes down into Kafka, and then there are a bunch of downstream ecosystem, including the warehouse that's listening to Kafka and continuously ingesting data into it. Scale is pretty amazing, 1.5 trillion messages per day, and a triple-digit number of machines that we've got deployed running Kafka here. But it turns out there's also other data. So this is all the data that we are generating from LinkedIn.com, right? When you come to LinkedIn.com, we generate a bunch of data, and we've got a pretty good handle on standardizing, hey, you use Espresso most of the time, and then you're using Kafka for tracking. But then we also acquire companies, and these companies are coming in from very different places. Some of them are running entirely on Amazon. Some of them have their own little data center. And so anytime we acquire a new company, it's a new data integration challenge. And so when we look at some of the recent acquisitions like SlideShare, Bizzo, Lynda are kind of three big ones that come to mind, their data lives in very different places. Some of it is in databases that we don't know how to run, but we know how to query. And then there's Amazon, the whole ecosystem. And some of it is actually in Kafka, so that's easy. Then there are other integrations as well. LinkedIn is not just LinkedIn.com and all its acquisitions. We also have salespeople, and we also have email marketers and a bunch of other departments that are doing a lot of business on Salesforce. Responses, Eloqua, these are a bunch of other marketing vendors we work with. And so those integrations also produce data, and that data is super important, and it's useful to integrate that with other data sets so that we can get interesting insights. And again, all of this data, again, lives in the cloud or special protocols. So this kind of motivated us to build a general purpose ingest system that could actually unify all our ingest that is happening, both for our internal data sets as well as for all these third-party data sets, into one single system. And we call that system Gobblin because it's gobbling in all of the data. And the big three requirements we had at the time was source diversity. That was obviously the easy one. And then batch and streaming, because we were already in this mixed mode of we have a bunch of data that is streaming and we have some data that is kind of batch, and it doesn't kind of make sense to continuously be polling on a filer for something that will arrive every night. And so we wanted to make sure that we had good support for both batch and streaming. And then finally, data quality, because that's one of the biggest things that happens every time you integrate with a data set. You have data quality issues the next day. So the Gobblin architecture is, standard, modular, layered. We've taken care to try to make everything replaceable and pluggable. But the two or three things that I wanted to point out here are the monitoring piece. So monitoring is something that is often kind of tacked on later to these systems, and we kind of made it a first-class citizen. So every single ingest pipeline has kind of first-class monitoring events coming out in real time, not just raw numbers, but literally custom events. So we can actually track how many records for a particular domain or for a particular kind of data set we ingested, even though the entire pipeline might be running very multi-tenant. And finally, at the lowest level, we made it pluggable where and how we run Gobblin. So there are use cases where we run Gobblin in single node mode, where it's just a few servers and Gobblin is running on those servers as just standalone instances. Or it runs on Hadoop using MapReduce. Or it can actually run on Yarn as a native app that's continuously running. And this was super important because, like I said, the diversity of sources requires us to bridge both kind of the batch worlds or the streaming worlds, as well as sometimes just organizational boundaries where, even though you can use Hadoop MapReduce, that doesn't mean we're going to allow the grid to reach out to this particular endpoint. And so we want to run this thing on a dedicated set of nodes where the firewall and the NetOps is signed off on the connectivity. And then the final piece that I think is interesting in Gobblin is kind of it has taken a metadata first kind of approach towards ingestion. So pretty much all of the configs are exposed as metadata entities, and we're trying to integrate with existing metadata stores to expose as well as document everything that's going on. So this is at a high level how Gobblin works. There's a concept of a source. A source is assumed to be partitionable. And so the source is responsible for generating work units. Each of these work units gets sent through a pipeline of extraction, conversion, quality checking, and then finally a writer. And then there's an data publish step, which can optionally be the barrier in case you want to have atomic guarantees between a batch of ingest and a batch of publishing data versus completely streaming. In that case, you would have a data publish that's continuously writing out. So Gobblin started out first as a batch system, and then recently we've been working on kind of solving for real time. And the reason we did that is the original pipeline that was bringing in Kafka data to Hadoop was based on MapReduce, right? It was running MapReduce every 10 minutes. And we realized that there's a ton of inefficiency in spawning up a job, getting slots, running a job for a few minutes, tearing down, and then within a few minutes again starting up. So if your source is continuous, you kind of want to be running continuously. But the gotcha with that is if you're running continuously, you have to always generally over-provision. You have to make sure that you can handle the peak traffic, otherwise you're going to be lagging. And so we've been working on kind of an interesting solution using Yarn for macro level resource allocation. So we use Yarn and get a bunch of containers. And then we use Apache Helix, which actually came out of LinkedIn as well, to bin pack work units into these containers. And these containers now run continuously, and we plan to enable auto-scaling now. So the ability for Helix to essentially realize that this set of containers are either under-provisioned or over-provisioned, work with Yarn to either relinquish containers back or get new containers, and then add more, rebalance the work units across the executor so that you can get more parallelism. So that's kind of work in progress that kind of shows how you can take a system that you first initially just operated on batch and then move it more towards supporting continuous and real-time ingest. Current activity, it's open source at GitHub. A fair number of companies have been kicking the tires. Some have actually publicly endorsed it. And at LinkedIn, it's 100 terabytes a day that we bring in. Pretty much all of our data gets ingested by Gobblin. And a few things we're working on is kind of doing streaming Hadoop to Hadoop copies, because we run Hadoop in lots of different data centers, and we want to have super fast data copies between them. And making everything metadata driven so that you have declared topologies for where data lands and where it goes. And Gobblin just executes that specification using its engines. So I'll spend, we've talked about ingest. I'm going to spend a small amount of time on the processing piece and then hand it over to Kapil to talk about serving. So Gobblin and UMP actually is kind of a hybrid of ingesting data into Hadoop. And Hadoop has had a long life cycle at LinkedIn, and it continues to be pretty strong. We started out with these very batchy data processing frameworks like Pig, Hive, and obviously MapReduce underneath it. But recent times, we've started moving towards Scalding, which is very programmer friendly. A lot of people like it because they can unit test it. There's still a lot of SQL holdouts at LinkedIn who would prefer that everyone writes Hive. And then there are people who kind of come in from programming in Java or Scala, and they love the fact that they can unit test their code and code in the IDE. So we're seeing a fair amount of diversity there. Two new entrants that deserve a fair bit of discussion are Spark and Samza. Spark, the graph below actually shows kind of how our usage of it has skyrocketed in the last few months. We actually did some interesting, we went back and looked at exactly when did this spike happen. And turned out this was when we enabled node labeling on our cluster so that people could actually execute Spark jobs against only the high memory nodes. So we run a heterogeneous Hadoop cluster where some of the nodes, most of the nodes are dirt cheap and therefore don't have a lot of memory. And then we sprinkle out a few high memory boxes as well. And so once we turned on node labeling, we found that people were super excited and wanted to try out Spark. So we've got more than 1,000 unique flows actually executing every day, which is pretty incredible. The primary use case for Spark has been machine learning, primarily because we get that huge speed up in terms of iteration time. Something that used to take 2 hours can now be done in like a few minutes. And that really brings down the training times of models to the kind of time frame where you can start thinking about, oh, I could actually train a model and then deploy it out in kind of real time. And that's pretty incredible. We're also looking at, obviously, Spark as general purpose ETL. The first time we looked at it, which was about a couple of years ago, we didn't see a huge difference. I mean, compared to the 50x improvement we see with machine learning, we were seeing about 2 to 5x improvement in regular just ETL workloads. But Spark has been improving quite a bit since then. And there's also this advantage of writing your code in one framework and not having to straddle between 2 or 3 different languages just because one part is machine learning, one part is ETL. So I think Spark has pretty much taken over the machine learning world, and I think it's starting to make some inroads into the ETL world as well. And Samza obviously comes from purely stream processing world when you're processing events at a time, and we use it a ton for real-time monitoring, for any kind of real-time standardization when you're updating your profile and you want to standardize it super quick into kind of our canonical definitions of what your title is, which company you work for. The Samza, compared to other stream processing engines, there are a lot of similarities and a few key differences. It uses Yarn for resource allocation, although I believe that's getting made pluggable as well. It uses Kafka and only Kafka for stream storage, and it kind of forces a materialization into Kafka between each stage, which is kind of an interesting decision. And the other big thing that SAMZA has decided to do, which distinguishes it from other stream processing frameworks really, is optimizing for this local state. So there's the opportunity to have a local RocksDB instance, typically is what we use, where you can actually keep local state. And anyone who's tried to do stream processing realizes that you can either bring the stream to the store or you can take the store to the stream. There are only two options. And oftentimes, stream processing frameworks that don't account for both actually result in having a bottleneck one way or the other. So you can have a database that tries to do stream processing, but it may have challenges in bringing the stream to it, or you can have a stream processing framework that has a problem with doing stateful stream processing because once you want to try to output your state, you're doing remote calls. And so SAMZA kind of tries to take a stream state integrated approach where you have a local state store that you can continuously write to at a super high throughput. And then there's more out there, right? The streaming ecosystem is super bubbly and frothy right now. Apache Storm has been there for a while. Kafka Streams recently came out. So a lot of these are somewhat low-level streaming abstractions, and then there are higher-level streaming abstractions that are getting built on top, which still include a runtime engine. And then there's Apache Beam, which we think has a lot of promise. It came from Google's Cloud Data Flow. Its approach is to basically not really take an approach of I'm going to mandate an execution engine, but to really say, let's focus on the abstractions and get those right. Because data processing is actually somewhat of a dark art. You have to account for late data, you have to account for reprocessing, you have to account for bad data, right? And then you also have to account for systems that claim to be exactly ones, but maybe are not really in certain error conditions. So Beam really is trying to create a kind of wrapper layer, and different frameworks are trying to plug into it. So that's pretty interesting. So that's, I think, the create, ingest, and process stages of our pipeline. And I'll hand it over to Kapil to talk about Pinot, which is our serving layer.
Yeah, thanks, Shashanka. So now that we have looked at the create, ingest, and the process phases of the real-time data pipeline at LinkedIn, let me spend some time talking about sort of the last phase, which is the real-time serving of that computed data. And I'm specifically going to focus on the OLAP serving engine that we built at LinkedIn and has been open source for some time now, called Pinot. So let's recap again, like some of these metric computation use cases, right? And this is the kind of applications that we are increasingly seeing on LinkedIn.com and becoming more and more popular, right? This particular one is who viewed my profile, right? And this is, again, both interactive, which means on LinkedIn.com, people can sort of slice and dice, look at this data. And it's also real time, which means if I go and look at somebody's profile, that data will be reflected in those results fairly soon, right? And something like Who Viewed My Profile lets you see not only the total amount of profile views that you've had, but also lets you slice and dice those metrics by any number of dimensions or combinations thereof. And this can be pretty interesting, right? Not only do you want to know how you're trending in terms of profile views, right? Did you get more profile views compared to last week? But you also want to know, where are these profile views coming from, right? How many of your profile views are coming from salespeople or recruiters or maybe, say, software professionals? Which geo are they coming from? Which industry are they coming from? And based on your profession, a lot of these insights can actually be quite valuable. Now, the first approach to solving a use case like this was, okay, let's just keep it simple and let's pre-compute everything, right? When you design an application or you design maybe even internal dashboarding use case, let's figure out all the possible dimensions that exist in your data set and look over the universe of questions and the queries the user can ask. Let's use one of your favorite data processing engines, among the ones Shashanka just described, and let's compute those, stick in a key value store, and whenever a user queries it, just serve back the result, right? So if you have, going back to the profile views, let's say the two interesting dimensions you care about are, which devices those views came from and which geos those came from. And that's a, tiny little data set that describes it. And, it's easy to compute all the possible ones. So you're going to compute, Android has total of 2 views, iOS has total of 1 view, so same for geos, and then all the combinations, so many for Android and US, so many for iOS and US, and so on. And actually, for some use cases where, the data sets are small enough and it's not very dimensional, this approach works just fine, especially operational metrics is one class of problems. But for a lot of data sets, as the number of dimension grows, as the data set sizes grows, the amount of pre-computation you have to do quickly explodes, right? Like this is just again a sort of toy example, which is showing the amount of explosion that happens to your data set as you go from just 2 dimensions to 3 dimensions. And most of our data sets at LinkedIn are of the order of billions of rows and hundreds, sometimes, and even more larger number of dimensions. So pre-computing this is pretty infeasible, and even if it is feasible, it's ridiculously expensive given the amount of computation that you have to perform to essentially figure that out. Now, I know many of you are probably going to wonder, well, this is not exactly a new problem, right? I mean, relational databases have been around for like decades, and they solve this and more complex class of problems. And while that is true, sometimes there are definitely cases when that additional complexity and the features that you don't really need in a way get in your way. But when we were designing for this class of applications, we also had a few, somewhat unique challenges. Right? First is, no matter what data sizes and traffic you start with, your data sizes are going to grow very quickly. So having a horizontally scalable architecture is incredibly important. Data freshness is super important for a lot of these use cases. Right? Forget about daily, but even if you load multiple times a day or even multiple times an hour, there are use cases where that simply does not suffice. You really have to make your real-time data available for querying. Many of these applications are site-facing, right? And that demands that your serving latencies be extremely low, of the order of milliseconds. And of course, I'll talk about some of the features like that you need for OLAP. And when we started, LinkedIn had this homegrown search index implementation called Sensei, which also supported a lot of faceting features. So the initial attempt at building an engine like this was to essentially take that search index, start removing unnecessary features, and rewrite some of the others. And that was really the first generation of Pinot. And more recently, we have done a lot of other changes. We rewrote a bunch of internals inside Pinot, which really allowed us to make much faster progress on adding some of the features. Now, there is a lot of features that we put in Pinot, and I'm not going to talk about all of it, but there are some that I think that are particularly crucial. One, it's SQL-like interface, and at least right now, we don't do like a full SQL join support. But just having that familiar language actually made a lot of difference from its adoption, just ease of use, the users being able to program against it. We talked about the sub-second query latency. That's extremely important. And real-time data loads from both Hadoop and Kafka so that you can make the streams queryable in real time. This is sort of the high-level flow that exists. Right? We have real-time streams that are coming in from Kafka and Espresso and so on and so forth. That data also gets ingested to Hadoop, and in both these places, we have processing engines that can operate on that data and compute derived data flows. And Pinot has the capability to ingest from both of these. So it's ingesting real-time data out of Kafka and batch data out of Hadoop. Now, you'll wonder, why do we need both of these? And the answer is, we move the recomputation of the indexes and the compactions off of the serving tier So we do that in Hadoop, and periodically we reload and refresh the segments inside of Pinot with the more optimally compressed indexes and segments. These are kind of the wide variety of applications that run on Pinot at LinkedIn. It's been in production since 2012. In 2015, we open sourced it. So we have multiple site-facing apps. We have internal reporting and experimentation dashboards, and real-time monitoring use cases internally that are all served out of Pinot today. Quickly going over the language, nothing fancy here, really. It's a fairly limited set of SQL, but that's sufficient for these use cases. We have basic operations on single tables, filter, ags, aggregation capabilities, doing order bys to get top Ks and things like that. And at an architecture level, from a deployment point of view, Pinot has like two kinds of nodes. One is what we call broker nodes, and the second is data nodes, which exist as real-time nodes as well as what we call historical nodes. And this is the data flow that I talked about earlier. And we typically run multi-tenant clusters, so we can run multiple use cases on the same, sort of a mini cloud, if you will, for operational ease. And Apache Helix, which is a generic cluster manager that we built internally at LinkedIn and then open source as Apache, plays a crucial role here. So the cluster usually just starts off like this, where you have empty nodes just marked as broker nodes or data nodes. And when you have a new use case that you want to deploy, you just start it as a declarative spec, and you say, okay, this is my new store, and I want so many data nodes, and I want so many brokers, and these are the replicas that I need for serving or just for like high availability. And Helix essentially just assigns those roles to those nodes and brings up the cluster. And from a scale point of view, we run like thousands of nodes of aggregate capacity. The largest node clusters are of the order of hundreds, and we have hundreds of stores as well. So it's a pretty diverse set of use cases. There are some that would fit almost on a single node. There are other use cases that need hundreds of nodes. And let's go skip this. From a storage point of view, I won't talk too much. I mean, there's a lot of standard innovations that have happened in the database world, including columnar storage. We break up columns into each individual column is broken up into what we call segments, compressed and stored separately to optimize on the storage format based on the data in that particular segment. And we choose from run length encoding, dictionary encoding, and many of the other common compression techniques that are available. We have a wide variety of indexing techniques using bitmaps, what we usually are called inverted index in the search world. We also have forward indexes like this that make some of the filter operations pretty easy. If you're filtering on model, for example, this is a cars data set, then instead of scanning the entire data set, which you still could do pretty quickly, you could just consult your forward index, get the, especially when the data set is sorted, and you could just go from the start to the end doc IDs and then continue with the rest of your processing, which might include further filtering and aggregation and so forth. Now, one of the, and from a deployment point of view, Pinot has been tremendously successful. We have hundreds of use cases in production. But typically for site-serving use cases, we also have to keep most of the data in memory, which can be pretty expensive. So over the last year, we actually have done a fair amount of improvements that really push the envelope in terms of how much data can we really efficiently serve out of a single node, so that we are not just limited to in-memory serving, but can also take advantages of spilling over the data to SSDs and things like that. And a lot of the other techniques like vectorization, sketching algorithms for approximate count distincts and things like that. So now we are there are still use cases where the real-time computation still tends to be expensive. So we are kind of back to our original choice of, should we pre-compute this large set of answers or leave the data as it is, like we've done in Pinot, and just compute those at runtime? And it's a trade-off, right? Do you spend a lot more cost on pre-computing answers which may never be asked for, or do you spend it on storing all this data in, in RAM? And one of the key innovations that we've been rolling out over the past year is, what we call data-aware pre-computation. And it goes something like this, where we let the data itself guide the organization of the data, the indexes. So we start branching on the dimensions which are naturally the most interesting and frequently offering in the data, right? So just to take an example, look at country dimension, and if you're looking at US, chances are you have a lot of data there. Most of your traffic is probably from the US, and that is not something you can afford to scan at runtime. So it might make sense to pre-compute that. But if you have a smaller data set, say country Zimbabwe, then you don't have to pre-compute it. You can just leave it as it is and just compute it on the fly. And we use that same principle as we keep branching this tree. So within US, we'll next branch on device. If you want it just on device, we'll sort of collapse that country dimension and start branching on device, and we build this tree out. And pretty much now any query can be answered by going through the tree, and if you find the answer at an intermediate node, you can answer it right away, or if you fall off through the leaf node, you can still scan it pretty quickly because we branch till we get to a point where the number of rows are small enough that you can quickly scan all of them. And that also enables us to do what we call active and real-time monitoring. And a lot of the monitoring use cases ultimately, end up looking like this, where we have all the real-time data in Pinot. We can query it and start building dashboards like this, where we take any business metric, and you can compute a week-over-week comparison. And you see that around April 3rd, there's a little bit of weakness. There's a decline in that particular metric. So now the analyst starts doing his cycle of, form a hypothesis, could it have come because of some device changes? Could it have come because of a particular geography or something else? And then you can quickly iterate against Pinot to slice and dice along those dimensions. But this still can be, a long process. But because of some of these innovations that I talked about, especially the data-aware pre-computation, where we can incrementally maintain the data structure, we can break the cycle and automatically start by generating heat maps that look like this. And we can simultaneously do this across multiple dimensions and to arbitrary depths. So instead of having to query the engine repeatedly, you start off by something like this. And it's easy to kind of spot that, there are a couple of cells there which are lighting up in red. That indicates a decline, and the stronger the color, the stronger the decline. So you can double click on that, and then you see the next set of dimensions, and using that you can much more quickly sort of figure out what is going on. Right? And that's what Pinot has kind of allowed us to do, and there's a lot of more work going on in all these layers that's really serving our end-to-end real-time data pipelines at LinkedIn. So to summarize quickly, we have we think of the real-time data ecosystem in these 4 phases of create, ingest, process, and serve. And we have made key innovations in each of these layers. And in many of these, we have open source projects that have been widely adopted. And so feel free to check those out. We have an engineering blog and the GitHub page as well. And I hope many of you find this useful in your day jobs as well. Thank you.